Thank you for giving me the opportunity to talk with you today. Being semi-retired and a geology adjunct professor at Oregon Coast Community College, the opportunity to teach or speak with professionals, citizen scientists, and volunteers outside of the classroom is rather infrequent. This talk is not being presented in person because of a prior commitment to give a talk about a model in development on predictive modeling of back beach erosion at Beverly and Moolock beaches for the Geological Society of America. So even though this is not a face-to-face presentation, my sincere hope is that you enjoy and learn something new from this recorded lecture. I hope you will forgive me for mispronunciation of place names. My only excuse is being raised and living most of my life in Texas, where we all, by fate of accent and stubbornness, mispronounce place names. This lecture is on the geology of the Oregon coast with emphasis on the headlands, islands, and the Cascadia subduction zone. This is a view of Cannon Beach from Ecola State Park viewpoint, showing an arcuate beach framed by headlands with sea stacks. I was asked to discuss a large range of topics for the presentation, so my goal is to give you a brief overview of each topic. The first topic is common rocks prevalent along the Oregon coastline. All rocks are made up of minerals. Minerals are compounds or elements that are homogeneous, naturally occurring, solid, inorganic, have a definable chemical composition and crystal structure. Geologists genetically identify or classify rocks according to their origin. Therefore, a rock is a naturally occurring solid substance composed of one or more minerals or mineraloids. Rocks can vary in size from tiny pebbles to massive mountains. They form through geological processes such as cooling and solidification of molten material that form igneous rocks, compaction and cementation of sediments from sedimentary rocks, or recrystallization of existing rocks due to heat and pressure forming metamorphic rocks. We use a genetic classification of rocks. Geologists use a genetic classification of rocks based on their formative processes. First, we will discuss igneous rocks. Igneous rocks form from the solidification of molten rock material. If they cool and solidify within the earth, they are called plutonic, and the molten rock they cool from is called magma. If the molten rock is extruded to the surface, it is called lava. The slower the rock cools, the more time the minerals have to grow, and the larger or more coarse grained the minerals become. Geologists call this texture phaneritic. Conversely, the quicker the mineral cools, the less time the mineral grows, and the smaller or more fine-grained the mineral is. For extruded lavas, the minerals are not visible to the eye because of rapid cooling. Geologists call this texture aphanitic. Each column in the chart shown is read from top down. Igneous rocks fall into four general groupings. From the right, ultramafic, mafic, intermediate, and felsic, based on their silica content and percent mineral content. Basalt is the dominant igneous rock along the Oregon coast. It is mafic in composition and contains between 46 and 54% silica. Basalts are composed of three minerals: olivine, pyroxene, plagioclase feldspar. Mafic igneous rocks dominate the coast. The coastal basalts originated from ancient lava flows that began in present-day eastern Oregon and Washington. Some originated from ancient tectonic ridges and plates, and others from four-arc basins. We will discuss this in more detail later in this talk. There are limited outcrops of gabbro, the intrusive or plutonic mafic rock. Most of the gabbros are found in sills and dikes along the Oregon coast. A dike cuts across pre-existing layers, usually along fractures, and a sill is injected parallel between beds or layers of rock. What are sedimentary rocks? Sedimentary rocks are formed by the deposition and precipitation of materials that come from the breakdown of older rocks. Weathering is a process that breaks down rock into sedimentary class and/or dissolves the rocks into ions and water. The diagram has three paths. The first path on the right forms clastic sedimentary rock from the physical breakdown of rock. The rock and mineral fragments are transported by water to a basin and are deposited, buried, and compacted to form clastic sedimentary rock. An example would be sandstone, the rock shown on the bottom right. Along the second path, the rock is chemically weathered by oxygen or rainwater into its constituent ions that attach to water molecules and are transported into groundwater or by river and streams to the oceans. When temperature change occurs, either hotter or cooler than their dissolution temperature, the ions precipitate out of the water and form evaporites like gypsum shown in the photo bottom left. On the third path, the original rock is chemically weathered and new minerals are formed. The minerals are cemented together to form a clastic sedimentary rock, such as an oolitic hematite shown in the photo in the center of the chart. Along the Oregon coast, you'll find several common sedimentary rocks. Let's explore them. Mudstone is prevalent along the Oregon coast. It forms from fine-grained sediments like silt and clay that accumulate over time. These rocks are often gray or black and have a smooth texture. Shale is another common sedimentary rock found in Oregon. It consists of compacted mud and clay particles. Shale can be easily split into thin layers and is often dark in color. 3. Siltstone is composed of fine-grained particles between sand and clay in size. It has a smooth texture and can be found in various coastal locations. Graywacke is a type of sandstone with abundant rock fragments and matrix material. It often contains angular grains and is commonly seen along the coast. And finally, tuff is a volcanic rock formed from ash and other volcanic debris. Along the Oregon coast, you'll find tuff deposits from ancient volcanic eruptions. Metamorphic rocks are any rocks that undergo changes due to temperature, pressure, or the presence of hot fluids that cause a solid state change in the rocks. A solid state change means the rock may both change its mineral composition and change the shape and/or orientation of the minerals. The most common metamorphic rocks found along our coastal shores include schist, gneiss, and marble. A schist is characterized by its foliated texture, often containing visible mineral grains aligned in layers. Gneiss exhibits alternating light and dark bands due to the recrystallization of minerals. Marble forms from the metamorphism of limestone and is known for its smooth texture and monomineral composition, calcium carbonate. Remnants of these ancient metamorphic rocks can be found on the cliffs, offshore rocks, and reefs at Coquille Point, Cape Blanco, Cape Sebastian, and Cape Ferrelo. Similar, very local blue schist or amphibolites, my favorite rock, occurs in the Port Orford shear zone on the beach west of Battle Rock at Port Orford. Next, we will have a brief discussion on plate tectonics, one of the most fundamental theories in geology. This is a view of Cape Arago or Arago, showing part of the headlands and sea stacks or islands. In 1912, the meteorologist Alfred Wegener amply described what he called continental drift, which he explained in his 1915 book, The Origin of Continents and Oceans, and thereafter a huge scientific debate started that would end that would end 50 years later in the theory of plate tectonics. Starting from the idea, also expressed by some of his forerunners, that the present continents once formed a single landmass, later to be called Pangaea. He stated that Pangaea drifted apart, thus releasing the continents from the Earth's mantle. He likened the moving continents to icebergs of low-density granite plowing through a sea of denser basalt. Wegener had some compelling evidence for his hypothesis. Number one, the continents seemed to fit together geographically. Number two, the distribution of climatic belts, both polar and equatorial, over the continent lined up or were associated when the continents were fit together. Number three, the distribution of similar fossils on the different southern continents that were not capable of swimming an ocean implied that the continents had been joined into a supercontinent. And four, rock assemblage match across the Atlantic, including mountain belts, geologic structures such as fold belts, rock types, and rock ages when the continents were mapped together. The geologist of his era reasoned that the Earth might have a solid crust, a mantle, and a liquid core. But there seemed to be no way that portions of the crust could move around. The geologist did not accept his hypothesis for two basic reasons. One, the lighter, less dense continents could not plow through the denser material or mantle. For example, you can't push paper through a table. And two, he did not provide a force sufficient to drive or move the continents. The theory of plate tectonics evolved in the 1960s. Previous research provided a strong foundation. First, of course, was Wegener's evidence supporting continental drift. Secondly was Hess-Dietz, the seafloor spreading hypothesis in 1960 that we will discuss in the following slides. By 1968, evidence for tectonics was overwhelming, and it was accepted as theory. This evidence changed the view of most geologists. Both Robert Dietz and Henry Hess had simultaneously articulated very similar theories about seafloor spreading. However, Hess is credited with the idea because he distributed a preprint of his ideas the year before Dietz's paper was published, which would ultimately become Hess's 1962 paper, History of the Ocean Basins. In addition, Hess had spent many years studying the mid-ocean ridges where Dietz had not. We now know, thanks to seismic tomography, sonar, and GPS, that the lithosphere, the rigid outer part of the Earth, consisting of the crust and upper mantle, is made up of about 20 separate plates or lithospheric plates. Of the 20 plates, about 12 of them are major plates with relatively large areas, and the rest are microplates. The Juan de Fuca plate is a microplate. There are two general types of plates, marine and a combination of marine composed of mafic material and continental plates composed of mostly felsic-derived rocks. There are three types of plate boundaries: convergent, collision zones where two plates come together; divergent, ridges where two plates separate and move in opposite direction; and transform boundaries where plates slide past one another, either in opposite directions or in the same relative direction but at different velocities. Plates move at a rate from 1 to 15 centimeters per year. Your fingernails grow at a rate of 2 centimeters per year. 2.5 centimeters equal 1 inch. As stated earlier, Wegener had not provided a mechanism for moving the continents for his hypothesis on continental drift in 1918. Arthur Holmes in 1944 first hypothesized about convection within the mantle. Hess in the 1950s propounded the idea of plate tectonics, which eventually became theory when mantle convection was proven by seismic tomography. Temperature at the bottom of the mantle is around 2,727 degrees centigrade, or 4,940 degrees Fahrenheit, and heats the lower mantle. The ultramafic rock of the lower mantle peridotite does not melt due to extreme pressure exerted on it, but the heat expands the rock and causes that volume of space to become less dense than the surrounding material. The heated material rises like a bubble in water through the asthenosphere, the upper layer of the Earth's mantle, below or beneath the lithosphere. There is relatively low resistance to plastic flow, and convection is thought to occur within the asthenosphere. As the convecting mantle moves beneath the lithosphere, it diverges and loses heat by conduction into the lithosphere. As the convecting mantle cools and moves away from the divergent zone, it becomes denser than the surrounding mantle material, and the lithosphere thickens. Eventually, the plate begins to sink back into the mantle due to its increased mass and density. It sinks towards the lower mantle core boundary, where it starts to heat up again, becomes less dense than the surrounding material, and rises again, creating a huge circulating convection cycle of solid but plastic rock. Envision a lava lamp. The lava lamp represents a large circulating tube of rock in the mantle as the wax rises and falls due to convection. When the upwelling mantle reaches about 60 kilometers depth, the plastic heated material does two things. It either melts and rises to the surface as magma and adds on to the diverging plates as new plate material, or it diverges at the top of the asthenosphere, pushes the lithospheric plate that rides upon it away from the divergent zone. Seafloor spreading opens the axial rift valley. Rising asthenosphere melts, forming mafic magma. The pooled magma solidifies into oceanic rock. Some structures associated with marine plates are pillar basalts, or pillar lavas rather, upwelling magma that is quenched at the sea floor, dikes, the solidified vertical or diagonally preserved magma conduits, and 3, the mafic plutonic rock gabbro from deeper magma that has cooled slowly. The average thickness of marine plates away from the rift zone is about 7 kilometers. Divergent boundaries are also characterized by earthquake and volcanism. The mid-ocean ridge lies about a kilometer beneath the ocean surface and about 2.4 kilometers or 8,000 feet above the ocean floor. As the plate moves apart, it breaks the ridge into a series of normal faults that drop down about a half a kilometer and form a rift valley from the separating plates. The slope of the ridge extends down on both sides for about 500 kilometers to the abyssal plain. The abyssal plain is the deepest and flattest portion of the ocean. The bottom of the marine crust is composed of the mafic phaneritic visible mineral grains in the igneous rock gabbro, Lying above this is the area of basalt dikes and a gabbroic matrices that are fed by conduits from the nearest magma chamber. As the magma reaches the surface, a layer of pillar lava erupts onto the surface. Pillar lavas are blobs of magma that cool rapidly when the lava encounters cold oceanic waters. On the other end of the plate are convergent boundaries. The new crust created at divergent boundaries along the rift is consumed at convergent boundaries. Convergent boundaries occur where two plates meet or converge together. One of the plates is always marine, and the other plate may be either marine or continental. If the two plates are marine, the marine plate that has traveled the furthest and cooled the most subducts beneath the other plate because it's denser. This subducting plate or downwarping plate is always denser of the two plates. The less dense plate cannot subduct and crumples along the boundary, creating an accretionary ridge. As the downgoing subducting plate reaches about 100 kilometers depth at the bottom of the lithosphere, the rock dehydrates. All the moisture in the rock, both physical and chemical, is removed from the rock and supersaturates the mantle rock above it. Water added to solid igneous rock lowers the melting temperature of the rock, and the magma, which is less dense than the surrounding rock, rises to the surface. The rising lava extrudes onto the surface, forming volcanic island arcs on marine plates. Examples of this are the Aleutian Islands, the Japanese Islands, and the Philippine-Malaysian Islands. If a continental plate abuts the downwarping plate, the rising magma forms continental volcanic arcs, like the Cascade Mountains and the Andes Mountains. Because of the collision that occur at convergent boundaries, they are characterized by earthquakes and volcanism. Sometimes a marginal sea or back-arc basin, a small ocean basin behind an island arc, forms either where subduction happens to begin very far offshore, trapping oceanic lithosphere behind the arc, or where the stretching of the lithosphere behind the arc leads to a formation of small spreading ridges behind the arc. J. Tuzo Wilson defined the term transform boundary. At transform boundaries, two plates or blocks of land slide past one another or shear past one another along huge vertical faults that extend towards the bottom of the lithosphere. This may be caused by two plates abutting but moving in opposite direction, or two plates or blocks of land that are moving in the same direction but at different velocities. All divergent zone boundaries are not long continuous lines, but are offset from one another in smaller segments. In the areas between the offset spreading ridges are transform boundaries. If a continental plate and a marine plate slide past one another going in opposite directions, it is called a transform boundary. The San Andreas Fault in California is an example of this. The North American plate is slowly rotating counterclockwise, and the Pacific plate is moving to the northwest. In addition to asthenosphere convection, two other forces drive plate motion. The first is ridge push force, an outward directed force that contributes to moving plates away from a mid-ocean ridge axis. It develops because the lithosphere of mid-ocean ridges lies at a higher elevation than that of the adjacent abyssal plains. The geometry of a mid-ocean ridge resembles a tilted glass of honey in that the surface of the seafloor lies higher along a mid-ocean ridge axis than the adjacent abyssal plain. Gravity causes the elevated lithosphere, or honey, at the ridge axis to push on the lithosphere that lies further from the axis, making it move away. As the lithosphere moves away from the ridge axis, new asthenosphere continuously rises, providing material from which new crust and new lithospheric mantle forms. The second force is slab pull force that arises simply because lithospheres that was formed more than 10 million years ago has become denser than the asthenosphere, so it can sink into the asthenosphere. Therefore, once any part of an oceanic plate starts to sink at a convergent boundary, it gradually pulls the rest of the plate along behind it, like an anchor pulling down its anchor line. The topic of discussion for this section is the geologic history of Oregon and the Oregon coast. The photograph is a view of Crook Point on the southernmost headlands on the Oregon coast. By the beginning of the Triassic period of the Mesozoic era, all the continents had united to form the supercontinent Pangaea. For tens of millions of years, the Earth had one hemisphere that was mostly continental, Pangaea, and the other entirely oceanic, the Panthalassic Ocean. The continent Pangaea was nearly divided by the Tethys Sea into two large northern and southern lands, Laurasia and Gondwana, respectively. Approaching from the west were the exotic terrains. A terrane is a crust fragment formed on a tectonic plate or broken off from it and accreted or sutured to crust lying on another plate. These exotic terranes would eventually form northern California, Oregon, and Washington, western British Columbia, and parts of Alaska. Animals of the early Triassic could have roamed across Laurasia from western North America, across Europe and Asia to the western Panthalassic Ocean. Pangaea was relatively short-lived and had pretty much broken up into our modern continents, with oceans separating them by the end of Triassic. First to separate was Gondwana, that divided into India, Australia, Antarctica, South America, and Africa. By early Jurassic, Laurasia had broken apart into North America, Europe, and Asia. The Atlantic Ocean has been widening due to rifting since early Jurassic. By Jurassic time, the western continental margin of the United States had existed for 600 million years. It accumulated enough sediment, 4,000 to 6,000 feet, during all these years to form a very broad coastal plain and continental shelf. This is a general timeline of major geologic events that formed the state of Oregon and consequently the modern Oregon coast. First was the accretion of the Klamath and Blue Mountains between late Triassic to early Cretaceous. The next major event was the erosion and deposition of Cretaceous sediments onto central Oregon from the erosion of the Klamath and Blue Mountains. Thirdly, we will discuss the formation of Celesia that began forming as a tectonic plate with seamounts during early Pale Eocene and was finally accreted onto Oregon and Washington by early Eocene. Many Oregon coast headlands were formed during this period. Finally, we will talk about the Columbia River flood basalts and its effect on creating some of our modern headlands. During the early geologic history of the central Oregon coast, at the close of the Mesozoic era, and through much of the Pale Eocene epoch, a large embayment occupied most of Oregon and Washington. The central Oregon coast was non-existent. The coastline in early Cenozoic, about 50 million years ago, was 250 miles east near John Day. Newport, Oregon would have been sitting on the continental shelf under 1,200 to 1,500 feet of water. Today, this depth would be comparable to riding on a boat 15 to 20 miles off the coast of Newport, Oregon. Oregon's oldest rocks originated as volcanic island arcs far out in the ocean, at a time when the Pacific Northwest coast ended near the present Oregon-Idaho border. These rocks are known as exotic terrains because they came from other places, riding on the floor of the Pacific Ocean as it subducted beneath North America. They were too big or too thick to easily slide beneath the edge of the North American continent. Instead, they remained in the subduction zone and welded themselves to the edge of the growing continental plate. The result we see today is a fascinating array of varied rocks, thick slices of oceanic crust, limestone with tropical corals, volcanic seamounts, shiny blue-green serpentinite, and large areas of totally crushed and broken rocks called melange. The melange is produced by the incredible forces at the contact between the subducting marine plate and the non-subducting continental plate smashing together. Although these rocks probably extend beneath the entire state, they are largely buried by younger rocks and can be found at the surface only in the Klamath Mountains and in northeast Oregon. By Cretaceous, the Blue Mountains and Klamath Mountains were accreted onto North America. The Blue Mountains' diverse geology includes a basement complex of terrains, fragments with distinct histories originating from ancient oceanic settings. Evidence suggests that during the Jurassic period, the Blue Mountains may have been connected to the Sierra Nevadas in the eastern Klamath Ranges, forming a continuous chain. Throughout the Cretaceous, the subduction trench jumped oceanward and sediments began to fill in the continental shelf and were deposited in various basins, including those associated with magmatic activity, oceanic environments, and tectonic processes. The rocks of the Klamath Mountains originated as island arcs and continental fragments in the Pacific Ocean. The island masses consisted of rifted fragments of pre-existing continents and volcanic islands created over subduction zones. These island masses contain rocks as old as 500 million years before present, dating to the early Paleozoic era. A succession of 8 island terrains moved eastward on the ancient Farallon Plate and collided with the North American Plate between 260 and about 130 million years ago. At the end of Cretaceous, the Farallon Plate was being consumed under North America. The remnants of that plate would be called the Juan de Fuca Plate. The subduction and collision of the Farallon Plate with North America contributed sedimentary wedges and volcanic arcs to both the Blue Mountains and the Klamath Mountain terrains. As the terrains of the Klamath Mountains were accreted or annexed to North America, the terrains were subjected to episodic clockwise rotation, intrusion by plutons, and faulting. The model above illustrates the rotation of the Blue Mountain terrains, the Klamath terrains, and the Northern Sierra terrain. Most rotation took place when the various terrains were offshore and before they were annexed to the North American continent. A smaller degree of tertiary rotation was due to the subduction of the Juan de Fuca Plate about 30 million years ago, and to the basin and range extension about 17 million years ago. By the early Cenozoic 55 million years ago, the Pacific Northwest had begun to approximate its present geographic configuration. The coastline ran from just north of the Klamath Mountains, arcing inland to present-day city of John Day, then continuing arcing into Washington to just east of the Vancouver Islands in Canada. Now we will discuss the formation and placement of the Celesia terrane, the last terrane to anneal onto western North America, which rode upon the last remnant of the Farallon Marine Plate, beginning in late Paleocene and completing its docking and rotation to its present position by the end of Eocene. The rocks of the Celesia terrane form the basement rock beneath the Coast Range, the Willamette Valley, and the Western Cascades. Finally, we will discuss volcanism of the Yachats and Cascade Head basalts formed on the seaward margin of the Four Arc Basin and the islands and eventual headlands they formed. The Celesia terrane is the last terrane to anneal onto the northwestern United States. The thickness of the terrane varies considerably beneath Oregon. It is 15 to 20 miles in thickness, while under Vancouver Island, the base of the terrane is less than 4 miles down. The western boundary of Celesia is the north-south trending right lateral transform Fulmore Fault. Under the eastern boundary in central Oregon, Celesia forms a platform on which the older, now defunct volcanoes of the Western Cascades rest. The younger high Cascades to the east are believed to rest on sediments that accumulated in the basin between Celesia and the continent. In southern Oregon, Celesia has been thrust against the Mesozoic Klamath Mountains of southern Oregon along the Klamath Blue Mountain lineament, KBML. During the Paleocene epoch, the northern divergent zone separating the northern remnant of the Farallon Plate moving to the southeast and the Kula Plate moving to the north trended east to west and intersected North America somewhere between present-day Portland, Oregon, and Tacoma, Washington. Two hypotheses prevail for the formation of Celesia. In Model 1, a superplume, probably the Yellowstone superplume, under a northeast trending divergent zone, had multiple eruptions that built seamounts in a massive volcanic plateau that was carried by the Farallon Plate to collide with and accrete onto North America. Because of the Farallon Plate motion was to the southeast and the North American Plate motion was to the northwest, the island arcs and plateaus struck the Oregon and Washington coast obliquely. The older terranes are located to the south near Roseburg and to the north around Vancouver Island. The younger terrain is located between. Model 2 is simpler, with volcanism occurring along the Mesozoic continental margin, where upwelling mantle material erupted at the transform boundary between North America and the eastern margin of the Farallon Plate and the Kula Plate. In support of this hypothesis, there is evidence that the erupted submarine basalts interfere with locally derived sediments from the continental land mass. Currently, the preponderance of evidence supports the Model A or Model 1 hypothesis. About 60 million years ago, a chain of volcanic islands and associated volcanic plateau named Celesia were carried atop the Farallon Plate and accreted onto North America at the red dashed line shown in the diagram. After docking, paleomagnetism testing indicated that the terrain rotated 35 degrees into its present position and subsided into a marine four-arc trough west of the emerging Cascades. The Celesia Basin rocks are about 15 miles thick. The Farallon Plate began to break up around 55 to 52 million years ago during the Eocene epoch. The Juan de Fuca plate is a remnant of the once vast Farallon plate and is referred to in the intervening phase as the Vancouver plate between the breakup of the Farallon plate and the activation of the San Andreas fault around 30 million years ago. All three plates subducted along the Cascadia subduction zone. Around 30 million years ago, the plates were stabilized into the three plates known today, the Gorda plate to the south, the Juan de Fuca plate in the middle, and the Explorer plate to the north. The diagram illustrates the evolution of the Juan de Fuca plate from the Farallon or Vancouver plate 30 million years ago. On the left to the present Juan de Fuca plate. The San Andreas fault began almost 30 million years ago when the Pacific plate intersected the North American plate to form a transform boundary. This is the view of a small island called Gull Rock off Cape Perpetua. In this final section, we will talk about the four geologic processes that created conditions for the formation of headlands and islands in Oregon. There are four processes whereby the formation of headlands can occur. 1. By wave action and differential erosion of the coastal exotic sedimentary terrains. 2. By uplift due to plate tectonics. 3. By creation of islands that accrete onto the coastline as headlands by volcanism. And 4. By volcanic intrusion or coastal flows of the Columbia River basalts. Sea stacks and islands are formed by wave action erosion of all the headlands created by the four processes mentioned. The image is of Cascade Head. Headlands and bays form on discordant coastlines where bands of rock of alternating resistance run perpendicular to the coast. Bays form when weak, less resistant rocks, such as siltstone and claystone, are eroded, leaving bands of stronger, more resistant rocks, such as sandstones and basalts, forming a headland or a peninsula. Headlands are characterized by high breaking waves, rocky shores, intense erosion, and steep sea cliffs. Rocky coasts have narrow or no beaches and rocky bluffs and cliffs. They experience more powerful waves from deeper nearshore water. The concentrated wave energy erodes sediment from the bluffs, and the high wave energy limits beach buildup. In the illustration, a headland protrudes into the sea and contains a tunnel labeled Sea Arch. The part of the headlands from the sea arch to the sea is labeled Future Sea Stack. Several rocky islands at the end of the eroded headlands are labeled Sea Stacks. The sandy area between the end of a headland and the sea stacks is labeled Tombolo. A cave cutting into the cliff is labeled Sea Cave. A sandy beach set back from the sea is labeled Embayment. The second image is an arch cut into Elephant Rock at Bend, Oregon. As stated earlier, exotic lands are land masses that have been transported and attached to a continent due to plate tectonics. They can form headlands when they are composed of rock types that are more resistant to erosion compared to the surrounding materials. Currently, these accreted lands from the south are the Yali Bali terrain, the Gold Beach terrain, Picket Peak terrain, the Elk subterrane, and the Sixes terrain, all subterranes of the Franciscan and Dolphin terrains of the southwest Oregon major terrains that compose the Klamath Mountains. The uplift of coastal mountain ranges by the collision of the non-subducting North American plate with the subducting Juan de Fuca plate can create headlands as the elevated land protrudes into the sea and is shaped by wave action. The photograph is the uplifted Astoria Formation with a basalt sill at Cape Coanda in Pacific City, a very fun place to explore. The third process is associated with the Columbia River Basalt Group. The Columbia River Basalt Group is a large igneous province that can form headlands and islands when the basaltic layers are exposed and eroded by oceanic processes. The drawing shows the ancestral drainage of the Columbia River that was repeatedly forced northward by the invasion of the Columbia River basalts. The Frenchman Springs flow marks the oldest course of the Columbia River. The Priest Rapid flow forced the Columbia River channel close to its present location. Here are two examples of Columbia River basalt that flowed to the Pacific Ocean. The photographs on the left is Yaquina Head, and the one on the right is Elephant Rock and its associated stacks at Seal Rock, Oregon. Ho and Cashman in 1997 characterized the 500-kilometer-long ginkgo flow of the Columbia River Basalt Group. They determined that it formed its terminus at Seal Rock roughly in a week, based on the measured melting temperature along the flow from the origin to the most distant point of the flow, combined with hydraulic considerations. What is a forearc basin? A forearc is the region between the oceanic trench and the associated volcanic arc. Forearc regions are found at the convergent margins and include any accretionary wedge and basin that may be present. Late Eocene Yachats basalt and Cascade Head basalt volcanism may have resulted from upwelling and decompressional melting of accreted Celesia mantle overlying the subducting slab during a short-lived period of local extension. Decompression melting triggered by extension in the forearc basin would have been promoted if the mantle wedge was also hotter in the tertiary period. Moore, in 2006, suggested that the lithospheric mantle beneath the Celesia may have remained hot for millions of years after becoming a part of the North American plate. The additional mantle wedge thickness and the transport of heat into the forearc basin from the circulating mantle of the Cascade subduction system would have also resulted in a warmer mantle source beneath the forearc basin. The timing of the Yachats basalt and Cascade Head basalt volcanism occurred during a period of plate reorganization in which the rate and direction of convergence were changing. These basins are formed between the oceanic trench and the volcanic arc in subduction zones. Islands can form within these basins due to the accumulation of sediments and volcanic materials. The island was then accreted onto the continent to form the headlands at Cape Perpetua, shown in the photograph, and Cascade Head. Geographically, an island is typically defined as a tract of land surrounded by water and smaller than a continent. However, there is no strict lower limit in terms of size. Islands can range from tiny islets or islets or rock outcrops to large land masses. Some very small islands may be just a few square meters in area. These are photographs of especially beautiful arches, sea stacks, and islands found on our rocky coast. Foreground Cape Coanda headland consists of massive to medium-bedded Arcosic sandstone from the Middle Miocene Astoria Formation. Haystack Rock is composed of remnant lavas from the intrusive Depot Bay basalt. Although the source of the Depot Bay basalt is not specifically known, it has been hypothesized that it may come from an earlier flow than the Ginkgo flow from the Frenchman Springs member of the Wanapum basalt group. Haystack Rock at Cannon Beach is a 235-foot tall sea stack composed of basalt from the same Ginkgo flow as found at Yaquina Head. Mac Reef and Arch, located along the southern Oregon coast, is primarily composed of sandstone. Thanks go to the United States Fish and Wildlife Service at this Rocky Shore training session for the opportunity to give this lecture to you about the geology of the Oregon coast, with emphasis on the headlands, islands, and the Cascadia subduction zone. If you have questions about geology or wish to make comments about this presentation, please don't hesitate to contact me at gilbertbernhardt@gmail.com. That's gilbertbernhardt@gmail.com. Thank you, and bye-bye.